Welcome back to another edition of our Liftoff webinar series. My name is Joe Steele. I'm the Senior Director of Communications and Legislative Affairs here with Lyft. Well, thank you for taking time to join us today and hear from Raytheon Technologies and a recent project they were working on with Lyft around efficient microstructure sensitive large deformation process modeling. That's a lot for me to say, but we'll leave it to Luke and Alex from the Raytheon team to explain that a little bit better as they get into their presentation. So I do want to take a couple of minutes to talk about some housekeeping items if we can. Everyone should be muted. If you're not, please go ahead and do so. I want to eliminate as much background noise as we can as we are recording this webinar, and we'll post it on the Lyft website at lyft.technology a little bit later today. So you can revisit it or send it along to folks that may not have been able to join us. If you do have a question throughout the presentation, please use the Q&A function. Please try to avoid using the chat function. If you can use the Q&A function on the Zoom toolbar, we'll be able to facilitate the Q&A when Luke and Alex are done with their presentation and get to as many questions as we can here in this hour. If not, we don't get to them all. We'll be sure to pass along any questions that come along to them and encourage you to follow up with those guys directly. So I do want to take a couple of minutes to talk about Lyft. Those who do not know who we are, what we do. Lyft is a Department of Defense Manufacturing Innovation Institute based here in Detroit. We are a nonprofit public-private partnership between industry, academia, and government. And our mission in life is to drive American manufacturing in the future through technology and talent development. We know that our future economic security and resiliency rests on advanced manufacturing. And we know that the next region or area that tackles advanced manufacturing first and masters advanced manufacturing is going to come out ahead. And we want that to be the USA, again, as we are a Department of Defense Manufacturing Innovation Institute. So we really want to help accelerate these technologies from concept into commercialization across the Valley of Death as quickly as possible to make sure that our warfighters and our industry can utilize them quicker and make use of them. So we are really solving the manufacturing equation. We work at the intersection of materials science, manufacturing process, systems engineering, and talent development. So really looking at manufacturing holistically, making sure we know what we need to make in the future. We know what we need to make it out of. We know how we need to make it. And we know at the end of the day, it's going to be fit for purpose in whatever system it's ending up in. And underneath all of that, we have the talent that can work on these new innovations. So really at Lyft, we have two programs, Leading Innovations for Tomorrow, which is our technology program, and Learning Innovations, which is our talent program. A little bit about the Leading Innovations for Tomorrow talent program. You see on your screen here the 4 pillars of technology under which all of our projects live. I'm not going to quiz you on this screen, but it shows you the breadth and depth of where our technology team is focused on and some of the areas of expertise we have both in-house and across our ecosystem, all the way from integrated computational materials engineering, working on the virtual side of things. So we didn't need to make and break things. We can virtually work on materials. We can virtually model and simulate them, to taking things into the physical world with advanced alloy and process development and multi-material joining. And then we're also looking at more agile and smarter manufacturing processes like wire arc additive manufacturing, cold spray. See all those things that we're working on. So if you haven't been to our Detroit facility, I encourage you to do so. If you have ideas that you're working on in these particular areas, please contact us and we can figure out ways to work with you. But come to the Detroit facility. We can show you our showcase and sandbox that we'll touch on a little bit later. On the talent side of the equation, this is still about innovating. It's still about bringing new techniques to bear, but it's really about new learning tools and new pathways and new venues. So that begins with our Lyft Learning Lab here at our Detroit facility. Again, this is perched above our high bay, so we bring students in of all ages to really take a look at advanced manufacturing, what that looks like in the year 2022. But then we offer Ignite Mastering Manufacturing, which is our high school curriculum, available to about 30, it's being used by about 3,500 students across the country right now to really give them foundational exposure to advanced manufacturing so they can begin the path to becoming the next generation of multi-skilled technicians so desperately needed in the advanced manufacturing world. But then we also offer certification courses for jobs that are available today for our more mature and adult learners. We have our own LIFT certified program where you see we offer certifications credentialed by the National Institute of Metalworking Skills, American Welding Society, and SACA on the robotics side. So welding, industrial technology maintenance, CNC machining, and robotics, the 4 majors that we work on. Then that also translates, those 4 majors translate into our Operation Next program, which was geared towards separating members of the military before they leave the service to allow them the opportunity to earn one of these credentials. So when they leave the service, they have a credential in hand, industry recognized, nationally portable credential, so they can go get a job in advanced manufacturing right away, begin their next mission after serving the military. It's available around the country, about 9 different locations, 9 or 10 different locations right now, National Guard and Reserve and their spouses, along with separating members of the military and their spouses and dependents. So one way we can give back to our service members. I mentioned we are a nonprofit public-private partnership. We're also a membership-based organization. We're thankful to have Raytheon as a member. But these are some of the things you can benefit from as a LIFT member. We're a trusted advisor, giving folks the best advice we can, both from our in-house experts and experts across the ecosystem in terms of how they can make that transition towards a smarter advanced manufacturing future. We're a technology accelerator, as I mentioned, trying to take these technologies from concept to commercialization as quickly as possible. I mentioned the technology showcase. If you have not visited us here in Detroit, please do. Really showcasing not only the art of the possible of what is next in advanced manufacturing, but really using it as a sandbox where we're working on some of those technologies and some of those processes each and every day. We're a connector and convener. So thank you very much for joining us today. That's why we're here, to bring the best minds available from industry, from government, from academia together to share what the future looks like for advanced manufacturing. Talent developer, we touched on that already, but again, new venues, new tools, new techniques to develop the future of advanced manufacturing education and the talent pipeline therein. And finally, we are a government partner. It can be tricky and unwieldy to work with the government, with the federal government. We are a conduit to help those businesses, particularly small, medium-sized businesses that may not be sure where to begin, but have an awesome idea or concept that can be used by the federal government. We are an avenue to do that. So I invite you to join us, invite you to reach out to us with any questions, comments, concerns. Follow us on our social channels, give us a call on the phone, send us an email, visit us on the website. We'd be happy to entertain and give you any additional information that you might need. So that is a little bit on LIFT. I'm going to turn the presentation now over to Luke on the Raytheon side to talk to us about the deformation progress or project that they were working on with LIFT. So Luke, the show is yours, sir.
Okay, thanks, Joe. And can you see my screen right now?
I can. If you go ahead and pop it in presentation mode, we'll be in great shape.
All right, perfect. All right, thank you for the introduction, Joe, and thank you for the opportunity to present the progress that we've made over the past several years at Raytheon Technologies in collaboration with LIFT over multiple phases of this project. And our goal has been to develop, as the title suggests, a microstructure-sensitive thermomechanical forming simulation capability. Essentially what this is a model, an ICME approach, which can simulate large deformation secondary processing events like forging, rolling, extrusion, and track the microstructure throughout this process throughout this process and enable us to predict the as received or as processed microstructure of a part that has been forged or rolled or extruded. This project, as I mentioned, has gone through multiple phases. Throughout the phases, we've had collaborators from universities, national labs, as well as software vendors, and also including LIFT itself. We've done some very valuable testing at LIFT. So there's been a lot of collaboration. We've really benefited from collaboration with all of these partners, especially LIFT, and you'll see some of the work that we've produced. This presentation mostly focuses on the simulation aspect of it, and it's informed by the test and characterization experiments. But most of the simulation work was done at the Research Center, at Raytheon Technologies Research Center, by myself, Masoud Anahid, and Alex Staroselsky, as well as Mark Renzulli. We also teamed with LS Dyna, or ANSYS LST, to implement some of the modeling capabilities that we developed into LS Dyna. And those collaborators included Wei Hu and Young Guo. And then, as I mentioned, we did testing at LIFT. John Keogh helped with that. And then in the most recent phase, Denise Vallis helped with the program management aspect of the program. So today I'll give a brief overview of Raytheon Technologies and how the Research Center, Raytheon Technologies Research Center, fits in to the corporation. And then I'll get into the technical talk, starting with the motivation, why we're interested in simulating the thermomechanical processing and consider the microstructure throughout of a specific material system, aluminum lithium 2070. I'll get into the model itself, how we calibrate it with focused experiments in microstructural characterization, and then discuss some of the validation. And the validation includes forging texture prediction for both homogeneous and heterogeneous deformation. I'll talk about why we, in the second phase of this project, why we focused on remeshing and the challenges associated with remeshing and remapping the microstructural variables. And then in the most recent phase of this program, we focused on improving the efficiency, because in order to have a model that's applicable to large-scale industrial forging or thermomechanical processing events, it needs to be efficient, because we're going to be running it on hundreds of thousands or maybe even millions of elements or integration points. And then I'll end with some concluding remarks. So Raytheon Technologies is composed of 4 different business units. The current company was formed a couple of years ago by combining United Technologies and Raytheon. And so we have currently 2 business units from Heritage United Technologies: Collins Aerospace, which makes aerospace components from nacelles to landing gear, wheels and brakes, and aircraft interiors. We also have Pratt & Whitney, which makes aircraft engines, both for commercial and aerospace, commercial and defense. And then Raytheon Intelligence in Space makes both air and space-based sensors, as well as cybersecurity capabilities. And then Raytheon Missiles and Defense makes precision missiles, radars, among other things. Raytheon Technologies Research Center, where Alex and I reside, is the central research hub of Raytheon Technologies. So we support the 4 business units, as well as government partners in DoD, DOE, as well as NASA. And we also support our various consortia that we're members of, including LIFT. And we do this by working on projects like I'll present today, and collaborating with many outside entities, including universities and national labs. Here are the technology focused areas of the Research Center. It spans everything from complex integrated systems, advanced materials and manufacturing, and electrification and sustainability. The talk I'll give today focuses on advanced materials and manufacturing. We're simulating a forging process and characterizing and simulating the evolution of the microstructure. So it fits right in this technology focus area of advanced materials and manufacturing. And it also fits within the ICME pillar of LIFT, as Joe presented earlier. So this work is motivated by one of our business units, Pratt & Whitney, developing and manufacturing aluminum lithium forged fan blades for their geared turbofan engines. In order to save weight because of the lower density of the lithium alloying agent, and by saving weight, you save fuel as well as increased durability. With aluminum lithium products, especially forged products, it's known that when you forge these products, you end up with heterogeneous and anisotropic behavior, and this is especially true in the inelastic and fracture behavior. So with this type of behavior, this type of microstructural evolution during processing, it's important to be able to predict the as received and location-specific microstructure throughout the part. And being able to predict that will allow you to design the process and also optimize it to achieve desirable microstructures in certain locations. For example, you can optimize a microstructure to achieve improved fatigue resistance in certain locations, or improved creep resistance or strength in other locations. In the model that I'll present today, it's part of a larger, more comprehensive durability modeling framework, which brings the processing parameters all the way to it brings predictive capabilities from the processing parameters through the microstructure and all the way to the in-service performance, including the prediction of the final life and performance of the parts. This is an overview of the program, actually the first phase of the program, which included several university collaborators. You can see all of the different components of the process, including mechanical constitutive tests, which were done at Ohio State University, as well as Case Western Reserve University. You'll see some of those tests in the talk today. And we also did a lot of microstructural analysis at University of Michigan and Ohio State University in order to characterize what was going on in the microstructure during the process, and then what the final microstructure looked like. There was also some dislocation dynamic modeling done at Lawrence Livermore National Labs to inform the hardening model that is used to predict the constitutive response and the texture evolution. And then the crystal plasticity model is what we focused on at the research center, and implementing this in finite element, calibrating it and validating it with constitutive tests, as well as forging experiments done both at the research center and at the LIFT High Bay. And then following the first phase, we implemented remeshing and remapping of the microstructural variables, and then improvement of the efficiency, and you'll see all of that in the subsequent slides. The foundation of the model is a crystal plasticity model based on large deformation formulation, where we multiplicatively decompose the deformation gradient, and the goal of this model is to predict the stress response to an input in strain or deformation, and also the texture evolution, how the grains are evolving in their orientation throughout the deformation process. And to do this, we have to calculate the slip rate, which is driven by the shear stress on the slip system, as well as hardening, dislocation, density, recrystallization, and temperature. So with any model, including crystal plasticity, we need calibration data. And for crystal plasticity models, you need the data at the grain level, because we're simulating the response at the grain level, and actually at the slip system level within the grain. So we need, as input to the model, calibration data for single crystals. Some materials exist in single crystal form, but others don't. The material system that we're focusing on for this program, aluminum lithium 2070, which is similar to the alloy that Pratt & Whitney is using for their aluminum lithium fan blades, it doesn't exist in single crystal form. So what we did is we designed focused experiments where we used a focused ion beam setup to mill a compression, a micro compression, and a micro shear specimen into grains of different orientations. And you can see these on the left-hand side here, the compression specimen, as well as the rail shear specimen. So these are milled into single grains or single crystals, and then we use the nano indenter to press on these in order to either subject it to compression or shear in the rail sections of the rail shear test. And by doing this and by combining it with either analytical or numerical calculations to account for the compliant substrate, we're able to fully characterize the stiffness matrix and provide important information, important parameters to the crystal plasticity model for the elastic behavior. In addition to using experiments and microstructural characterization to calibrate the model, we also used it to inform the physics, which we use to simulate the behavior. And this was done in collaboration with Case Western Reserve, who did some compression tests, and then University of Michigan, who did the microstructural characterization and analysis. And this was motivated by observations during compression testing that we saw softening in the response. And we wanted to know why the material was softening during high temperature compression. So we did interrupted tests at multiple total strains, and then we sectioned, polished, and imaged these sections in order to see what was going on with the microstructure, specifically how the microstructure was recrystallizing. And you can see in these images in the center of the screen for 0% strain using a grain orientation spread analysis, we characterized the recrystallized grains at about 15% area fraction, whereas at 100% we saw about 30% recrystallized grains. And so this provides evidence that there's recrystallization occurring during the deformation process, and we could also characterize the texture, the orientation of the recrystallized grains with respect to, and compare that to their parent grains. And we found that while the recrystallization affects the softening behavior, the constitutive response, it doesn't affect the texture significantly because the recrystallized grains have a similar texture as the parent grains. So that informed the additional physics that we use to enhance the crystal plasticity constitutive model, including dynamic recovery, which includes the effect of the density of both mobile and pin dislocations, their interactions with one another, their creation, annihilation, and so forth, as well as the effect of recrystallization, which we accounted for using an isotropic plasticity term shown in gray here, where the evolution of recrystallized grains characterized using the microstructural analysis that I presented, it affects the constitutive response through the plastic deformation gradient, but it doesn't affect the texture evolution based off of what we discovered in the microstructural analysis. So integrating these two additional equations in physics, we are able to calibrate the model based off of the stress strain response that we saw from Glebal tests that were conducted at Ohio State University at multiple strain rates and multiple temperatures, 3 temperatures specifically, 350, 400, and 450 C. And we calibrate at each temperature to 3 strain rates simultaneously to characterize the strain rate dependence of the material. And as you can see, for these two temperatures, we're able to calibrate the model very well. We're able to capture the softening behavior that's a result of the recovery and recrystallization. And then following calibration, we validated the model at an unseen or uncalibrated temperature, 425 degrees C, again at the same 3 strain rates, and we were able to predict the response very well. So we're confident we had a well-calibrated model, and we're capturing the necessary physics in order to simulate the constitutive response. Once we had calibrated the model in compression, we moved to validated in tension. We had some tensile tests at multiple temperatures from room temperature to 425 C, where we observed very different deformation responses as well as failure responses. So we simulated this using our crystal plasticity model. We were able to capture the stress strain response fairly well. And then we also used the crystal plasticity model to investigate some interesting behavior that we observed in the sample at 370 C, which experienced significant necking. And with the specimen, we sectioned it and we characterized the texture at different locations in the gauge section. And we found that in the deformed region, we got a typical tensile texture, but then very close to the fracture surface where the material is necking significantly, we observed an interesting texture. And we were able to use the crystal plasticity model to figure out what type of deformation was contributing to this interesting texture. And we found that it was a combination of uniaxial tension as well as shear. And based off this, we could predict the texture both in the form of inverse pole figures as well as pole figures for this specific location, which was very useful. Once we had calibrated, validated the model for both compression and tension uniaxial cases, we wanted to predict a forging texture. We had received these H forgings shown on the right here from Arconic, and these had 3 different sections, A, B, and C, of different thicknesses. And we started by trying to predict the texture in the region C. And by looking at the microstructure in this section, we could see that it wasn't simply a plane strain compression type forging, because we know what that texture looks like. We can predict it, shown in the bottom here. But there were additional components, Gauss texture components in these pole figures, showing that something else was happening besides just plane strain compression, or something was happening in the microstructure we didn't know initially. So we looked at the microstructure in detail in order to figure out whether the Gauss texture, the high Gauss texture, was coming from recrystallization, which sometimes is attributed to, which sometimes the Gauss texture is attributed to, or whether it came from the deformation history itself. So doing a grain orientation spread analysis, again, we could separate out the recrystallized grains from the deformed grains. We found that the area fraction of the recrystallized grains was really small. It was less than 5%. So it would be hard for these grains to contribute significantly to a Gauss type texture. And also, using this analysis, we can separate out the grains that have a Gauss texture from the other grains. And we found that these green grains have the Gauss type texture. And these are obviously large deformed grains. So we knew from this analysis that the Gauss texture was coming from the deformation. So we need to figure out what deformation steps would lead to this type of texture. So we used the model and we worked with the vendor to determine the sets of the set of operation steps, the processing steps that led to this texture, as well as the relative deformation magnitudes. And we found that the H forging goes through a 3-step process: an A upset, a B upset, and then a draw and step of the preform process, which is like a plane strain compression type test. And based off this, we could predict the texture very well. The forged texture is on the top here. The predicted texture is on the bottom. You can see that we're capturing all of the major texture components, and they're for the most part in the correct locations and in orientations and so forth. So the model did a really good job. It also helped us figure out why there was a rotation in the pole figure. We initially thought from the experiments that the specimen was rotated in the SEM, but by simulating this process, we found that because of shear due to the anisotropic material behavior, it can rotate the pole figure. So this was purely from the deformation process and not from any rotation of the specimen in the SEM. And then in addition to predicting the pull figures, we could also predict the relative concentrations or area fractions of the major components of texture from Gauss, including copper, S, brass, and cube, and we could predict the relative area fractions in this particular microstructure. And the model did a good job in predicting that. Oops. So once we had simulated the homogeneous forging in that H forging in the location where we focused, the deformation field was fairly homogeneous. So we wanted to further test the model on a heterogeneous deformation field. So we designed these experiments where we forge a 1/2-inch cube billet using a punch in a channel, either with an elliptical or an airfoil cutout, so that we achieve a heterogeneous deformation field. We forge this at high temperatures, at a forging temperature, and then we can characterize the microstructure. You can see here the heterogeneous deformation field in this microstructure from the grain flow. And you can see 4 different locations where we characterize the microstructure. And all 4 of these locations experience a different deformation history, and therefore will have a different as received or as produced microstructure. We first simulated this process using ANSYS. We built the crystal plasticity model into a user material subroutine. We integrated that with ANSYS, and we tried to simulate the process. We had some difficulties in simulating the process because of convergence issues with ANSYS and not having remeshing at this point in time. So we had to come up with some workarounds. We had to change the initial aspect ratio of the elements so that their final aspect ratio wasn't too great and we would experience convergence issues. We also had to use reduce integration elements, and then we had to zero out or turn off friction because that was causing too much shear at the interface between the die and the billet. But with all of these workarounds, we're able to do a good job at predicting the load versus deflection curve, where you can see the simulation result is below or lower than the experimental result, mainly because of the lack of friction. And then the texture, we were able to do a good job at predicting most of the major texture components. And I'm showing the texture at location 1 and at location 4, which are representative of all of the 4 locations. The major components were predicted for the most part in the right location of the right magnitude, relative magnitude, but there was definitely some room for improvement at this point in the project. And we determined that it would be necessary to include remeshing because these simulations have very large deformation. It's hard for a mesh to stay a good quality throughout that deformation process. When you're subjecting the billet to over 100% strain, you have some elements that experience very large deformation and distortion and can become issues with convergence for the finite element simulation. So at this phase in the project, we worked with the developers at LS-DYNA to utilize their 3D adaptivity functionality. And we combined our developed and calibrated validated crystal plasticity model with their FEA remeshing and remapping, and then also considering the microstructural features and their evolution throughout the deformation process. And putting this all together, we could predict the as-produced microstructure, the location-specific as-produced microstructure of large forgings or other thermomechanical process parts. The first challenge in doing this was to come up with appropriate remapping techniques. With these additivity or remeshing capabilities in various finite element packages, they have default remapping techniques. There's FEA remapping, which just uses the shape functions in the FEA mesh to remap the field variables from the stress to strain and also displacement and so forth. There's also more advanced methods, like in LS-DYNA, they have an element-free Galerkin, EFG, which is the default remapping method. But all of these remapping methods are meant for continuous variables in linear space, and they work pretty well. And they're essentially, linear interpolation based approaches. However, they don't work for microstructural parameters for a couple of reasons. One is that a microstructure is discrete. It's not continuous like we assume stress or strain or displacement is. It's discontinuous. So if you interpolate between two microstructures, you'll create a new microstructure that didn't exist before, which is unphysical and will cause problems with the prediction of the microstructural evolution. And then also, some of the microstructure parameters aren't represented in linear space. Like the texture is represented in spherical space. So we can't simply linearly interpolate between two textures, because we'll get the data will be jumbled. We'll get essentially garbage out of the interpolation, and that's what's shown in this first column here, where we did a simple remapping between around 1,000 elements to around 3,500 elements of a cube with no deformation. So the remapping should reproduce the original texture. You can see the default remapping didn't do a good job. So we came up with a couple of different approaches. One was a simple closest point projection. It's like a nearest neighbor projection method, where between the old mesh and the new mesh, the integration point in the new mesh simply found the integration point, the closest integration point in the old mesh, and took that microstructure and all of its parameters, including its texture, its deformation history, and all of the other parameters that are associated with describing its microstructure and prior deformation. We also came up with a Monte Carlo remapping technique, which not only considered the distance between the integration points in the new and the old mesh, but also the relative size of the elements themselves, and assigned appropriate weights to each integration point in the old mesh, and then randomly assigned based off of those weights an integration point, the microstructural parameters at an integration point from the old mesh to the new mesh. And we found that both of these techniques worked pretty well. In some scenarios, Monte Carlo method worked a little better than the closest point projection, but for the most part, both worked very well in mapping the old microstructure, the microstructure in the old mesh to that of the new mesh, without losing much information at all. And then, so once we had the model implemented in LS-DYNA, and we use the appropriate remapping techniques, we could simulate the forging of both the elliptical and the airfoil cross sections using this approach. And you can see the animation running now. And if you look closely, you can see that it's remeshing throughout this process. I'll run the animation one more time. So you can see about halfway through the simulation, you start to see remeshing. You can look at the elements at the top corners of the ellipse forging. You can see that the elements start to get distorted, then you start to get remeshing, and then later on, it's the elements in this region here that I'm pointing to that are triggering the remeshing. And the remeshing is being triggered by element quality. And there's a couple different options that you can use in LS-DYNA. We're using a shear deformation quality to trigger remeshing, which seemed to work pretty well and allowed us to simulate the whole process from 0 to about 100% global applied compressive strain. And then throughout this process, we're simulating the evolution of the microstructure. So at every single element, at every single integration point, we're simulating how the texture and microstructure is evolving, how plastic deformation is building up inside the material, and how that affects its current material behavior. by simulating this process with remeshing, we're able to more easily run the simulation with appropriate elements, and also to consider friction, appropriately considering friction based off of characterization tests that we did. And by doing this, we could more accurately predict the texture. And we predicted the texture at the same 4 locations shown in the image in the upper right. I'm showing 2 of the locations here, location 1 and location 4. And you can see that the texture prediction is much better than the previous one because of the added capabilities of the model. And you can see the majority of the major texture components are being predicted accurately in the correct location and of the correct magnitude, relative magnitude. So this was an improvement over the previous capability, and having remeshing really made simulating these processes much easier and more accurate. I mentioned that with remeshing, we're able to simulate the correct friction coefficient in order to better predict what's happening at the interface. So there's elements at the interface get sheared quite a bit because of the friction, and it also contributes to the global load deflection curve. I mean, you can see the difference between the previous simulation where we didn't have remeshing and we didn't have friction on the left, and the simulation where we had remeshing and we're able to consider friction. It does a much better job at predicting the load displacement behavior. There is still some discrepancy, and we think this is because the friction actually changes with time. You can see the experiment increases more gradually. The experimental force increases more gradually. We think that's because the boron nitride lubricant that we're using gets rubbed off during the forging process, and we saw that in the dies. Whereas in the simulation, we consider a constant friction coefficient. With the crystal plasticity model, we simulate the behavior at the crystal level, so we can predict the deformation, the plasticity at this level, and store this for plotting. And that's what we did here, where we're plotting the equivalent plastic strain, which is like a von Mises plastic strain, and we can homogenize this up to the integration point level and plot it as a state variable. And something interesting was observed when we did this. We could clearly see a shear band forming starting around 50% global strain, and then increasing in magnitude up to the final strain of about 92.5%. And you can see in this region, as well as in the flash, there's significant plastic deformation. And I mentioned while we were looking at those animations that the deformation in this region, in this V, is what's triggering remeshing. And you can see in this region, there's several 100% plastic strain, and it's really shearing these elements. So without remeshing, we're only able to achieve about 60% global deformation before the model lost convergence and it wouldn't run anymore. So it's important in this type of simulation to have remeshing so you can actually complete the simulation, the forging simulation, but also so you can have an accurate prediction and good element quality throughout. The most recent phase of this project focused on taking the model that I just presented that we validated on forging exercises and improving its efficiency. Running crystal plasticity at every single integration point is relatively expensive. So we want to make sure this model is as efficient as possible, so we can do this for hundreds of thousands or even over 1 million elements for an actual industrial forging simulation to forge an actual part. So we focused on first taking this model, which had been implemented as a proof of concept, so there wasn't a lot of focus initially on its efficiency, and it was implemented in the SMP paradigm in LS-DYNA, which is a shared memory processing, which limits you to one computer. You can run on multiple cores, but only on a single computer. We took that and we integrated that with MPP, massively parallel processing, and changed the code and the remapping accordingly. We also improved the efficiency of the code itself, and we found that for increasing model sizes, we tested this on 8.7K, 87K, and 887K element models, we increase the speed up significantly. So the larger model you go to, the more speed up you get. And the maximum speed up that we quantified was for a model with 887,000 elements, and we quantified a speed up of 17.1 times. And this was using the speed up that we achieved from going to MPP, but also we utilized some software engineering practices to improve the efficiency of the code itself, because the crystal plasticity code was the bottleneck in these simulations. So to put this in perspective, the 887,000 element model, it would have taken 140 days to run using the old code in SMP, but with the speed up, we could run it in 8 days. So this means that you can run large scale microstructure sensitive forming simulations in a reasonable amount of time, and then with the accuracy that I just presented. We validated the model using tests that were conducted at the lift high bay, using their 300-ton interlocking servo press with heated tooling. They forged airfoil cross-section specimens where the billet had material flow in all directions. You can see the billets that they forged here. They came out really well. And we replicated this process using the simulation capabilities, where I'm showing on the right-hand side here animation, the forging process without the top die. So you can see how it's being forged. And in the bottom here, you can see that we use remeshing. It improved the element quality, especially initially in the corners of the billet where the elements initially get really distorted and can affect the convergence of the model. So in conclusion, our goal was to develop a capable and efficient thermomechanical processing simulation approach that could predict the as-received microstructure and properties of a forged aluminum lithium part. We developed, calibrated, and validated the crystal plasticity model. We found that we had to enhance the crystal plasticity model to account for the constitutive behavior. We also had to incorporate remeshing in order to properly account for the element distortion that occurs and compensate for that with remeshing and remapping. And then finally, we improved the efficiency of the model to facilitate large-scale industrial forging or thermomechanical processing simulation while predicting the microstructure throughout. And then I'll end on this slide, which has contact information for myself, as well as Alex Staroselsky, who was the PI for this project. And if we don't get to all the questions today, you can feel free to reach out to us directly.
Awesome. Hey, Luke, thank you very much for the presentation. A lot of good information there. I did have a couple of questions that came in, but if you do have a question, please go ahead and enter it in the Q&A function. You'll see on the Zoom toolbar that we're all too familiar with these days. You'll see the Q&A or the chat. Please go ahead and use the Q&A. There were some questions that came in. I know Alex was chatting a little bit on the side here as well, but I want to make sure that everyone got the benefit of the questions and answers as well. But going back to the 989 and the 3548 remeshing, how long did it take for the remeshing at those element levels?
For the how long does it take the remeshing to happen?
Yeah.
It doesn't take very long. I don't think we ever quantified it because it's such a small part of the total simulation time. Yeah, it's for, I mean, and we try to minimize the number of remeshing steps. So in the 3D forging, there was only 3. In this one, there was only 3 remeshing steps. In the other one of the ellipse here, I think there were maybe 8 or so. And this is a simulation that takes, I think, 12 hours, and a very small fraction of it is remeshing. We're just using the built-in capabilities in Alstina for the remeshing. We're using the volumetric remeshing. So it basically takes the current volume as a geometry, remeshes it entirely using new TED elements, and then goes forward with that.
Got it. How do you determine the initial starting texture of the microstructure?
We always do EBSD analyses, so similar to what let me see if I can find. So yeah, similar to what I'm showing here, we do SEM and EBSD to characterize the microstructure, and you can extract the texture from this, and then we typically will sample from that texture randomly and create the initial microstructure. And we did go through some convergence analysis to determine how many grains we need to represent at each integration point. That's something I didn't present here, but each integration point has a number of grains, and we use a Taylor model to account for their contribution to the integration point, constitutive response, and texture and so forth. So we sample from that original texture from the EBSD, and then we use that in our model. So it's all experimentally characterized.
Got it. Got it. We have time for maybe one or two more. Do you need to assume an initial dislocation density in the virgin material? And if so, how was that determined?
Oh, it was taken, so it was taken from the literature, and during the deformation, dislocation density increased in I don't remember, 2 or 3 orders of magnitude. So details of initial dislocation density is not very important.
Got it. Got it. Got it. Okay. All right. And again, if you have, you want to go back to this slide that has your contact information, we can certainly have folks follow up with you directly if they want to go into more detail or have some additional follow-ups for you on the presentation. But we certainly appreciate you guys taking the time today. Certainly appreciate your partnership. Certainly appreciate you working with Lyft, and glad we're able to do some of that work here at our Detroit facility. So I encourage people to come out and visit us if they have not done so, and see what we've got going on here. But again, I think that's it for the questions at the moment. If folks want to reach out with these guys directly, please do so. You see their contact information on the screen. And I'm sure they would be happy to get back to you. In the meantime, give folks a couple minutes back in their day, and please stay tuned to your emails for our next liftoff webinar scheduled for July 12th with our friends at the Aluminum Extruders Council. But in the meantime, thank you to Luke, thank you to Alex, and thank you to Raytheon for the presentation day. Certainly appreciate it.
Thank you, Joe.
Thank you very much.
Thanks all. Have a great day.
Bye-bye.